In this problem, we're told to find the reaction force in this right here, this bar right here, BC, and the reaction force in pin D. Um, this problem is actually pretty straightforward if you recognize one important thing is that this bar or this handle or this arm is actually a three-force member. So what you can do is actually draw just this component, and I can show you why this is just a three-force member. So we could draw this component, looks something like this. So we have the handle, not handle, but the arm of this mechanism. It looks something like that. And what we can do, we can draw the forces on this diagram. So pin D typically has a y direction reaction force and an x directional reaction force, but we actually could simplify this problem quite easily because we know the compressive force is actually going vertically upward as shown in this diagram. Actually, it's going downward because it's a compressive force. So it's the compressive force is actually going downward here, and we know that when you push on this handle over here, you're only causing a horizontal force on C. So if you know that as well, that's going to be C. That must mean if you draw the line of action of this diagram of each force, you draw the line of action, and these are perpendicular to each other. And since the only other force acting on this arm is pin D, that must mean this there's only three forces acting on this arm, meaning it's a three-force member. So one of the things that you can do with three-force members is that all the forces must be concurrent or parallel. Since these forces already are not parallel, they must be concurrent. So what I'm saying is that if we draw a dashed line from here, this is the pin D, we could draw a dashed line to where they intersect to the other forces, so something like that. That must mean pin D, its force must point in that line of action. So what we could say is that D goes in that direction. And I define these forces arbitrarily. Again, as long as you're consistent with your signs and you get the math correct, you should get the same answers. So now that we have that, this becomes a pretty straightforward problem. So what we can do is now we need to find the angle at which D is being acted upon. So this will be angle theta. So what we can do is look at this diagram. So we're actually looking at this triangle right here. So this right here, we're looking at this triangle right here. So we want to find this angle theta. So that's very simple. So let me draw that triangle right here. So that's theta. So that must be the side length right here is 30 millimeters. So that'll be 30. And this side length will be 50. So our angle theta is simply the tan inverse of 3 over 5, which is going to be 30.964 degrees. So now that we have that, we could do our simple equilibrium equations. We don't need the idea of a moment because we don't need that. We only need the sum of the forces in the y and x direction. So we'll sum the forces in the x direction, and I'll define our axes in this fashion. So this will be y and x. So the sum of the forces in the x direction, we have a positive c. F points vertically downward. So d, the x component of d is simply negative d cosine of theta, and that equals 0. We have two unknowns, so we need another equation to solve this problem. So we'll take the sum of the forces in the y direction. So that'll be c points horizontally, so that doesn't count. So it'll be negative f, and then we have positive d sine theta, and that equals 0. And we know F, the compressive force, is 200 newtons, so we could say that d sine theta equals F. So then dF divided by sine theta will be 388.730 newtons. So now that we have that, we could find the reaction force at C. So C would equal d cosine theta. So that will be simply 388.730 times the cosine of 30.964 degrees. And what that equals is 333.332 newtons. And that'll be the reaction force. So more clearly, I could say that D, these are the answers, D is equal to 388.730 newtons, and C is 333.332 newtons. So to quickly recap of this problem, to make this problem a lot simpler, all you have to do is recognize that this arm right here, DCF, is actually a 3-force member. And we know that because the compressive force acts perpendicular to the surface of contact. So we're squeezing this or compressing this whatever object this is, which causes a reaction force on this pin that points directly downward. Well, it's not a pin, it's actually a bolt, but we'll get to that. And then we have here this reaction force at C, and the only force being applied to that is in the horizontal direction because of this handle. So you're screwing this downward, which causes a horizontal force in that direction. So we know those two forces, therefore we know that pin D, its reaction force must be concurrent with the other two forces, which is right here. So that's where all the forces line up to be. And once we know that, we could just apply our equilibrium equations. Once we know the angle at which D acts upon the pin D, and from there we could use our equilibrium equations to find the forces D and C.